So this presentation here is meant to guide you through the chi-squared test that you will do as part of collecting your data for the fruit fly F2 generation. But because we're getting into the topic of statistical testing, it's worth going over just the basics of statistics. You might have had statistics in other classes before. You might not have a lot of experience with statistics. We will talk about specifically one test called the chi-squared test and its application to evaluating whether the predictions we made about the ratios of your offspring are consistent with what could have been expected under natural outcomes. Or maybe if we have to seek a different explanation for the data. So the chi-squared test is our major topic, but we'll introduce statistical testing, specifically the chi-squared test. We'll set it up and do some examples and talk about how to evaluate the outcome. So we'll do this with sample data and then toward the end get into what you might be doing with your fruit fly data from your dihybrid cross. So chi-squared test is a form of statistical test, and it basically involves applying a numerical criterion to helping you make a decision. So we use this in science to generate probabilities that what we observe is consistent with what could have happened in nature versus maybe observing something that's not consistent with expectations and then needing a different explanation for it. So here's a good example, I think, from humans. This is a family of 14 kids, and every single one of those kids is a boy. So if we apply a simple expectation that every child has a 50% chance of becoming a boy or a girl, we've done this before in probability. What are the chances that you get boy, followed by boy, followed by boy, followed by boy, followed by boy, and so on? It becomes really, really rare. This is 1/2 raised to the 14th power, which ends up being a very small number indeed. And relative to the other possible outcomes here, we can see the probability of observing a single-sex family. This distribution here, this shows that most families, if we have families of 14, of which I can't imagine there are too many, families of 14, mostly under this expectation of 50% chance of boy or girl, mostly those are going to be somewhere close to this mean of 50%, half boys, half girls. And as we get farther away from that, it's less likely. So this is the frequency that these kinds of families would be observed. It's also the probability that you would run into such a family. So very good chance if you have a family of 14, you'll see it somewhere between 3/4 girls and 3/4 boys. That's most of the families you observe. And then it gets really, really rare, maybe all boys and one girl, or say 13 boys and one girl. But this chance of being all boys shows up, it looks just like 0 really on this graph. It's really, really rare by our expectations. And so if you observe this in your data, you might say, well, maybe my prediction of 50% boys and 50% girls, maybe that doesn't hold up for this family. And so that might cause you to look for another explanation. So one such test we can do is the chi-squared test to see if our predictions are consistent with expectations. We'll come back to this family toward the end. So statistical testing and chi-squared testing also requires us to think about our hypotheses. So when you run an experiment, you might not have thought of your fruit fly cross as an experiment very much, but we're basically testing predictions about how those offspring are going to come out. And these predictions are your hypotheses. It's basically an informed guess about what you think your offspring are going to look like. And every time we do a statistical test, we're evaluating competing hypotheses, 2 possible explanations for the data. And the first one we'll talk about is called the null hypothesis. This one doesn't often get a lot of attention. When you run a standard experiment or a typical experiment, you're often more interested in disproving the null hypothesis than you are supporting the null hypothesis. This is, as a null hypothesis, null means basically nothing, or not very interesting, or no, no surprises. And we're actually, with the fruit fly crosses and the chi-squared test, we're actually going to look, you'll be a little more satisfied if you end up supporting your null hypothesis. And that's kind of a rare case. You're probably trained, if you're familiar with p-values, you've been trained on trying to disprove the null hypothesis. And in our experiment, we're hoping to actually support the null hypothesis. That means that what you observe is consistent with what you predicted you were going to observe. So the reason we have statistical testing in biology and other sciences is that it's not very likely that we're going to measure an exact amount. So if you predict to find 3/4 of your offspring having a particular phenotype, you often don't have exactly 3/4 of one kind and 1/4 of another. You might have some variation around that. So that's where the statistical test comes in. So the null hypothesis for us is basically that your predictions are consistent with the data, and the alternative hypothesis gets this notation of H1 to contrast with the H0 null hypothesis. The alternative hypothesis is basically that the null hypothesis is not enough to explain, is not sufficient to explain the data. And so if you thought you had a particular kind of inheritance, say complete dominance on genes, and you observed a different ratio of offspring than you expected, you might have to have a different explanation. So if you had complete dominance of an autosomal gene, maybe you discover that you have incomplete dominance, or more than one gene contributing to the phenotype, or sex linkage, or so on. You might be surprised because there's something biological happening that's just not something you accounted for in your explanation. Another possibility, and one that a little more often gets called for on the student experiments, is something went wrong with the experiment. So I like to remind my students that they're doing something for the first time. They don't have a lot of technical prowess at it when they're first getting started. It's likely that we misidentified a fly. Some flies died that shouldn't have. Some of the phenotypes were not scored correctly, and so on. We might see this where we're rejecting the null hypothesis for some reason that we can't really explain at the end of it. So that might happen if we do the experiment well, and often it takes some practice to get good at fruit fly experiments. But if you do the experiment well, you should be able to support your hypotheses with statistical data. Let's find out about some samples here. So here's an example, simple example looking at just one gene. And if we cross these parents that are heterozygous for the scarlet gene, we see that we've got heterozygous parents, and we would predict, go ahead and do a little Punnett square for us here. If each parent has the ST plus allele and the ST allele, ST plus ST, ST plus ST, ST plus ST, ST, ST. So any of these that has at least one of the plus dominant allele gets the wild type eye color, and this kind gets the scarlet eye color. So we can use these as predicted ratios, right? 3/4 of our offspring we expect to have the wild type eye color, and 1/4 of the offspring we expect to have the scarlet eye color. So in this, let's say we count a number of offspring. Our null hypothesis is that the number of wild type offspring is going to be about 3/4 of the total, and the number of scarlet offspring is going to be about 1/4 of the total. So whatever that total is, we should be able to observe this 3/4, 1/4. And the question really becomes, how far can we get from exactly 3/4 before maybe this prediction is not as well supported. So say we're closer to 50-50, 1/2 and 1/2, that would be possibly too far away from the predicted ratios, and we'd have to seek a different explanation for this. So maybe we got the genotypes of the parents wrong, for example. All right, so our null hypothesis is that these are the ratios we will observe. And the alternative hypothesis is that something is going on biologically besides what we predicted, or we made a mistake, and we're not going to observe this 3/4, 1/4 ratio. Okay, so let's say we run the experiment, we caught 100 fruit flies. So if we expected 3/4 and 1/4, part of the statistical test involves predicting a specific number of offspring. So statistical tests are more powerful if you observe more individuals. So if you count 100 offspring, that's more powerful than counting 10 offspring. And increasing, if you go to 1,000 offspring, you get more statistical power. Basically, you have more confidence in the reality of this difference, and you can get more precise estimates. So we're going to do an example that has 100 fruit flies. And so if we had 100 fruit flies, the expected number, we're going to imagine that we knew we were going to get 100 fruit flies and anticipate how many of those would have been wild type phenotype and scarlet phenotype. So simply, we're just going to take 3/4 or 0.75, multiply that by 100, 75, and 1/4 of those would be 100 or 25 individuals. So the total still adds up to 100. That's important for this test. And each category has a corresponding expected number with it. So the chi-squared test has a rather convoluted formula. Might look scary at beginning, but it's not too much to worry about. Let's see if we can break it down. So that chi-squared, this is the Greek letter chi, looks like an X, makes a sound. Chi-squared. And so we don't have to worry about substituting anything in for these. This is just the symbol that tells us what kind of test we're running. Is equal to the sum, that's a capital letter sigma, to sum over all values of this equation, observed minus expected squared, all that over expected. Not too hard, right? So let's do an example here. So observed minus expected, 78 minus 75, that is 3. 22 minus 25, -3. The 0 here, I guess if we are totaling up 2 categories, we are 3 more than we expected in the wild type category, 3 fewer than we expected in the scarlet category. Everything evens out. Don't really have to worry about taking the total there. This next column, things get a little complicated. So we're looking at 9, or 3 squared, over the expected number 75. Down here, we've got -3 squared, so that conveniently makes everything a positive, even though we were -3 in this column. And now in this category, the total expected was 25. So let me get my calculator out here. 9 over 75 is 0.12. And 9 over 25 is 0.36. So this value, the sum of these two numbers, gets us 0.48. So that's our chi-squared value. That's the summary value for this chi-squared test. We're going to use that to evaluate what it means moving forward. So 0.48 is our chi-squared value. Just a little bit before we move on, just to get familiar with the chi-squared value, chi-squared numbers are bigger if we are farther away from our expectations. And that's very simply just the number in the numerator here is the difference between observed and expected. So if that difference is big, the numerator gets big, it's squared, makes it even bigger. and then divided by the expected. So if it's large relative to the expected, you get a big number for that category, and you might get a big number across all categories. If the chi-squared value is low, that means the observed and the expected were relatively close to each other, and the difference between them was relatively small. So just kind of, if you're mystified by the numbers, you can just think about big or small. So big is far from expectations, small is closer to expectations. So once we get our chi-squared value, then we have to convert it into a p-value. And I'll talk about p-value on the next slide. P-value is an estimate of the probability of observing the results given the, if the null hypothesis is true, basically. And we look up the p-value in a table like this. You can just do a web search like I did for chi-squared table. And what it shows is across the top, these are sample p-values. So p goes between 1 and 0. So very high p-values over here, decreasing, decreasing, decreasing to very low p-values on the right. And those are corresponding chi-squared values within. And each row has what we call a degrees of freedom entry. And degrees of freedom is a metric for this test. It's the number of categories that you're counting minus 1. So ours is 2 categories. The flies were either wild type eyes or scarlet eyes. 2 categories minus 1 gets us a degree of freedom of 1. So here's our example. We had a chi-squared value of 0.48 and 1 degree of freedom. We would follow the first row across until we find a pair of numbers that our number is in between. So it's not too far from this 0.45, but it's somewhere in between 0.45 and 2.71 is the value of our chi-squared. And that translates into a p-value between 0.5 and 0.1. And people, more than just reporting a range of p-values, they're typically interested to know, as I have over here, which side of 0.05 did we fall on? So 0.05 is kind of a standard cutoff across the sciences. It's 1 in 20, and it's generally thought that if something happens, is perceived to be less likely than 1 out of 20 times, then that's significantly different from expectations. So we are falling above 0.1. So you can write your number as p greater than 0.1. That's a nice way to summarize this value. So we don't know exactly what it is, but we know it's greater than 0.1, and we know that 0.1 is greater than 0.05. So that'll lead us to interpret our results in a different way. So again, the p-value is a probability. When we do the p-value for the chi-square, we're interested to know what are the chances that your predicted ratios basically are correct or could have happened. Are you close enough to your predictions? So a high p-value means that you have a good chance of being close to your predictions. So high probability results are consistent with predictions. And another way that's sometimes is summarized is that we should accept the null hypothesis. So again, null hypothesis was our predicted ratios. If we have a fairly high p-value, really anything in this range greater than 0.05, that's good enough to say, okay, well, we could have observed this, could be true, move on with our lives. If we get a low p-value, that means that it's pretty low chance that what we observed could have happened if our mode of inheritance was correct. So if we predicted correctly, it's pretty unlikely that we would have observed this kind of outcome. And so that causes us to say, well, something went wrong. Either we made the wrong prediction, we didn't understand the way that the alleles and phenotypes are inherited, what have you. It basically, in this example, causes us to seek a new explanation. That explanation could be that we didn't set up the experiment correctly, that there was one parent that was misidentified, there was one female that happened to have mated before we isolated her, so on. Lots of ways for experiments to go wrong. Less likely that experiments go wrong after you've got some experience with them. but doing experiments on fruit flies for the first time, maybe not the highest confidence in what we're doing. So low p-values cause us to reject the null hypothesis and try to find another explanation for the data. All right, so coming back to our family of 14, how likely is it that a family of 14 is all boys? And I guess I ran this once and the numbers were just too clean if we assumed a 50% outcome for boys and girls. And turns out if you survey across humans across the world, basically under natural conditions, if everything else is equal and boys and girls are treated the same in the womb all the way to birth, then there's actually a little bit greater chance that the child's going to come out a boy. So I don't have a good explanation for that right now, but things can be funky when it comes to meiosis and sperm competition and things. So maybe somebody else has a good answer about this, but there's just a little bit better chance of having a boy over a girl under natural conditions, so with no interference, as I say. So that would cause us, here we have 51.2% chance of having a boy. Makes our expectation now not just 7 out of 14 children on average, but 7.17 children to be boys. And this is, I think, helpful also because it could happen that when you calculate your predictions, you get a decimal prediction. So you may say, well, I counted 250 fruit flies, and I ended up expecting that 143.6 were going to be wild type phenotype. That's okay. So we're getting a number at the end of this. We're not getting a realistic expectation that there are going to be somehow 7 1/5 children born into this family. Okay, so keep that number in mind, 717. That's our expectation. Expected 6.83 girls. That's two numbers that add up to 14. So these are the expectations, very close numbers of boys and girls. But in fact, 14 boys, 0 girls. So in this family, we can compare this to our expectation, calculate these. So this is the difference between 14 and 717 squared divided by 717. And the sum of those is 13.33. That's our chi-squared summary value. Still have degrees of freedom equals 1 because we have 2 categories, boys and girls. And our calculation of 13.33 is bigger than the biggest number in the row. So that means that we are at least a p-value. Now we're heading in the less than direction. P is at least less than 0.005. And that was in the territory of very unlikely. So even less likely than 1 out of 200 chance of this happening. All right, coming back to fruit flies. This is something similar to what you might be calculating. This example, we worked it through. This is a cross involving the ruby gene, which is R there, and the brown gene. And the ruby gene is X-linked, so it's located on the X chromosome. And these are some sample numbers you might get for offspring. Just a reminder, as you're collecting the data for your flies, you want to keep track of the sex of the fly as well as its eye color. And we're going to run the chi-square test only on the eye color, but you want to, in the name of collecting complete data, you want to collect data about all of this, sex and eye color. You'll notice on this one, at least, there's some interesting patterns with the sex linkage. So for example, there are no ruby-eyed females, there are no light brown-eyed females, but we can still calculate out our expectations without taking sex into account. So take the same data and boil it down to just the eye color phenotype. And let's say instead of acknowledging the sex linkage in this case, we just predicted a standard autosomal outcome for these ratios. 9/16 of the offspring to have the wild type eye color, 3/16 to have the ruby eye, 3/16 brown eye, and 1/16 to have this double mutant color, which ended up being a light brown eye in this cross. So we took the same data, put them here, summarized by eye color, then our expectations are those fractions. 9/16 times the total number of flies that were counted, 256, gets us 144, and so on. 3/16 gets us 48, 1/16 gets us 16. And each row gets its own summary value. This is a low chi-square, 49 and 48 are very close to each other. This is a high chi-square value, so 33 versus 48, those are pretty far off from each other. So again, each row gets a summary part of the chi-squared equation, and then this 12.070, that's the sum of all numbers in the column. That's our actual chi-squared value. So how many degrees of freedom do we have now? In this case, we have 4 phenotypic categories that can give us now 3 degrees of freedom. So the degrees of freedom, basically that means that if you're putting into more categories, there's more room for variation to throw off your expectations. It's sort of like a statistical wiggle room. So if we follow down to the 3 degrees of freedom row, it's a little bit more forgiving. So these larger chi-square values are allowable for the same p cutoff. So our value, 12.070, follow the degrees of freedom 3 row across, 12.070, 12.0. All right, so we're not off the chart, but we're pretty close to it. In between these numbers, 0.01 and 0.005. And again, you would summarize your p-value and say, we don't know exactly what p is, but we know that it's less than 0.01, right?